In this video, we're going to look at an introduction to proofs. So a proof is a valid argument that establishes the truth of a statement. And in my opinion, proofs is what makes mathematics superior to every other subject, because in math, we can prove we are right. And even in science, when you collect data, there are still opportunities for your original hypothesis to change based on new data and new technology, but not in math. So proofs are really important for computer science. And in fact, I went ahead and listed some of the applications. It helps verify programs are correct. It establishes operating systems are secure, enables programs to make inferences with artificial intelligence, and shows that system specifications are consistent. So just a few applications of proofs and why you're being taught them. So there are some definitions here related to proofs: a theorem, lemma, conjecture, corollary, propositions. I'll let you read through those. They're not so important for this section. And if you've taken like calculus, you've probably seen some of these terminology in calculus. So I'm not going to belabor that. What I am more interested in us looking at is some kind of basic types of proving. What we're going to look at in this section primarily is proofs of if-then statement. Okay, so these are the kind of proofs we're looking at. So the first type is a trivial proof. If we know Q is true, then P implies Q is true. A vacacious proof: if we know P is false, then P implies Q is true as well. A direct proof: that means we start with our first statement and work our way to the conclusion. Proof by contraposition: that means that we start by looking at not Q implies not P. And proving this proves P implies Q. That's contraposition. Okay. And then proof by contradiction, which is also called reductio ad absurdum. That means we assume something is true and show that we get an absurdity or a false statement, okay, or a contradiction. We're going to look at all of these. Before we do, though, I want to comment on trivial proof and vacacious proof. So those actually follow from the truth table for P implies Q. So this is back in section 1.1 when we looked at the truth table for P implies Q. So here's P, here's Q, P implies Q. We would go true, true, false, false, true, false, true, false. And the only one of these that doesn't come out true is this second one, when we have true implies false, a true thing giving us a false statement. Okay, that means that these arguments, all right, are all going to provide for us validity. So if we happen to know that P is true, if we happen to know that Q is true, there we go, that's what I meant to say. If we happen to know that Q is true, like it is in those two cases right there, in both of those cases, Q is true, we automatically get a true argument. And that's what trivial proof is. The trivial proof says, if we happen to know Q is true, then we're done. Like there's nothing else to do. If we know the conclusion is true, we're done. The other case, the one case that has a true statement, is if we happen to know that P is false. In both cases where P is false, the argument comes out true as well. So those two cases are the vacacious proof. All right. So when we know P is false, we happen to know that the argument will work. There we go. It wasn't letting me highlight. Okay, cool. So there we go. That's kind of the I'm just going to we're not going to go through any trivial or vacacious proofs because they're kind of boring. There's no point in going through them if we know something happens to be true. We are going to go through direct proof, contraposition, and contradiction. All right. So we'll spend some time doing some examples on those. Before we do, real quick definition. We often use in number theory the idea of even versus odd. Okay, so an integer is even if we can write it in this form as 2 times a number. Okay, and n is odd if we can write it in this form, 2k plus 1. So basically it's like an even number plus 1. Okay, we'll use that when we're doing number theory proofs, which is quite a few proofs we'll see. So let's look at an example right off the bat that uses this. And they're telling us to use a direct proof. So give a direct proof. If n is an odd integer, then n squared is odd. Okay, so direct proof means we start with the first statement, the if statement. And I'm starting with if n is odd. So assume n is odd. And that means there exists an integer. Wow, sorry, that's not how you spell integer. An integer. Wow, that's not how you spell integer either. Integer k, such that n equals 2k plus 1. I'm basically just using the statement up here from n equals odd. There exists a case such that, okay, I like literally use that statement. I just use the definition of odd. Okay, cool. So that's the information I know. Now we're trying to show that when you square n, you get an odd number. So I'm going to go ahead and square this. So n squared equals 2k plus 1 squared. And if I FOIL that out, that's going to be 4k squared plus 4k plus 1. And if it's been a while since you've done FOIL, go watch a video, but I'm just distributing twice. I'm doing 2k plus 1 times 2k plus 1. All right, if it's been a while. Oh man, I just can't let it go. So you would just distribute 2k and then 1 and then combine the like terms. Okay, if it's been a while, there you go. So here's what we're looking at then. Now here's what I want to do. I want this thing that I'm staring at right here, I want it to be this form. I want it to look like an odd number. Now, what's really nice is I actually already have a plus 1. So I have a plus 1 here, and that I want to leave alone. What I'm going to do is I'm going to look at this first part here. And if I factor out a 2, what I'm left with is 2k squared plus 2k plus 1. And if I'd like, I can go ahead and call this a new number. How about I call it r? Let r equal 2k squared plus 2k. Then n squared equals 2r plus 1, which is an odd number. Oops. Which means I'm running out of space. N is an odd number. And I'm done with my proof. Okay, when I end my proofs, I like to put a little square at the end to indicate that I'm finished. Some textbooks do like a little square. Sometimes they do other indicators. A real classic end of proof indicator is called QED. I don't remember what that stands for. One time, oh, sorry, that's QED. One time my teacher told me, and I can't, it's like a Latin thing. All right. So it's just a nice way of saying I'm done. I've proven what I have been asked, and this is the finish of it. Okay. Let's try another one. This time, though, we're going to talk about what it means for something to be rational. Let me go ahead and get rid of this little. There. Okay. I knew it was going to be upset at me. That's fine. All right. So, sorry. The real number is rational if there exists integers p and q, where q doesn't equal 0, such that r equals p over q. So to be rational means you can write the number as a fraction. That's what rational means. And that's what they've done. They wrote r as a fraction. Okay. So here we go. Prove that the sum of two rational numbers gives us a rational number. All right. Proof. Oops. Let me switch to red. Sorry. Okay, so I'm going to assume, I'm going to do a direct proof again. Assume that, here, we'll call it R and S are rational numbers. That means R equals P over Q, and S equals T over U. For integers P, Q, T, U, where Q doesn't equal 0 and U doesn't equal 0. Okay, so I used the definition of a rational number. I made them into fraction form. R is P over Q, S is T over U, and I just made sure to state that all of those parts are integers and that the two denominators are not 0. Cool. All right, so this says we're going to sum them, so I'm going to add these two things together. So R plus S equals PQ plus T over U. Now, I happen to know from algebra, I can add these two together by getting an LCD, right? I can multiply this term by U and this term by Q, and that gives me an LCD. So I'm going to kind of skip all the steps and just do UP plus TQ over UQ. But I can go ahead and I'm kind of done, but I'm going to go ahead and call these two their own variables. All right, so I'm going to call this numerator V and this denominator W, where V equals UP plus TQ and W equals UQ, which happens to not equal 0 because both U and Q don't equal 0. Therefore, the sum of R and S is rational. And we're done. Now, what we've done here is generalized proving. I randomly chose some arbitrary rational number called R and another arbitrary rational number called S. And all I know is that because they're rational, they look like fractions, and I gave them a form. This is that universal generalization strategy. Because I've chosen these to be just some random rational numbers, I have proven it's true for every single rational number out there. If I add them together, I can do the same process of getting an LCD or getting a common denominator, adding them together and creating a new rational expression. All right. It's just labels. We're just putting labels in and making them fit the definitions. Okay, so let's move on to the different type of proof technique. Let's use contraposition. Now, let me just remind you what contraposition is. Contraposition means if I want to show that P implies Q, I'm instead going to show that not Q implies not P. That's what I'm going to show instead. So I'm going to look at this statement, the second statement, and by showing that starting with not Q and ending up with not P, I'm going to show this is the case because I used contraposition. Okay, so let's do it. So here's what we got. In this case, we want to prove if n is an integer and 3n plus 2 is odd, then n is odd. Okay, so just so we're clear, this first line, that's P. And this second line, that's Q. So I'm going to assume not Q. I'm going to assume n is not odd, which means I'm going to assume n is even. That is two S's that look weird. Sorry, let me zoom in just a smidge. Assume n is even. Okay. Now we know how even numbers look. Then there exists an integer k such that, oops, such that n equals 2k. That's the form for integer by that definition earlier. Cool. Now, what we want to do is we want to look at what happens to 3n plus 2. So let's consider 3n plus 2. Then, if I plug in 2k for the n, that's going to end up giving me 6k plus 2. And what I want to do is I want to show that this comes out even. And the reason I want to show it comes out even is because I'm doing the opposite, the negation. So just like I assumed n is even, I want the result to come out even. So I want this to come out even. So even numbers look like 2 times something. In this case, this is the something, 2 times 3k plus 1. So I'll call that, how about m? 2m, where m equals 3k plus 1, which means, oops, which means 3n plus 2 is even. So by contraposition, when 3n plus 2 is odd, n is also odd. And I'm done. So I ended my proof by stating what they were asking me to show. I did skip the fact that they just said n was an integer, but it's okay. Got a little bit lazy. It's fine. No big deal. Okay, so let's try another contraposition proof. Prove that for an integer n, if n squared is odd, then n is odd. Okay, so again, same kind of basic format, right? We're gonna do the opposite in the opposite order. So since this is P and this is Q, I'm going to assume not Q. So I'm going to assume n is not odd. In other words, I'm going to assume n is even. Okay, so I'm going to start with that. Assume n is even. Then there exists an integer k such that, oops, n equals 2k. Again, we want to look at n squared. Consider n squared. Then n squared equals 2k squared, which is 4k squared, which is 2 times 2k squared. So we have just shown that n squared equals 2 times another number. I'll call that other number. I'll even use the same letter I used last time, m, where m equals 2k squared. Then, or let's say therefore, n squared is even. So by contraposition, when n squared is odd, n is odd. And we're done. All right, so there you go. Contraposition. Assume the opposite of the conclusion, show that it gives us opposite of the assumed portion, and then we're able to go ahead and use contraposition. Okay, let's do contradiction. Contradiction is a little bit more of an art form. And I'm going to start us with like the most famous example of proof by contradiction. This is like the proof I learned when I did proof by contradiction. Okay, let's dive in. So proof by contradiction kind of starts off a little by like contraposition, except when we start stepping through it, we won't get the opposite of what we're trying to show. We'll end up getting some absurdity. So we start similarly. Use proof by contradiction to prove that square root of 2 is irrational. All right, so we're going to assume the opposite. That's proof by contradiction. Assume square root of 2 is rational. Well, that's actually useful because we have a definition of rational numbers. Then there exists integers P and Q such that the square root of 2 equals P over Q. And make sure that we say that Q doesn't equal 0. All right. So here's what we're going to do. We don't have much to work with, but we do have this. So I'm going to work with this now, use like some algebra, and see if I can produce something weird. So first thing I'm going to do is, I guess, go ahead and get rid of the square root. So I'm going to square both sides. I'm going to go ahead and just do a series of math. So this is going to be P squared over Q squared. Cool. All right. Then if I multiply or clear the fraction, I get 2Q squared equals P squared. Okay, now look at this. That means if I put this in parentheses, that means P squared is even. I'm not gonna, which means P squared is an even number. So I could take a second and call that M. I could just say, okay, that means that 2 times M equals P squared, where M is Q squared. I could do that. I can take that moment. Okay. But it's the same idea, which means P squared is an even number. So if you have a square that is an even number divisible by 2, okay, that actually has to mean that the original number is also divisible by 2. Think about it. If I square an odd number, if I take an odd number and square it, I'm going to get an odd number every time because I can't automatically get a factor of 2 in there that's going to magically make it, sorry, my brain shut off there. That's going to magically make it divisible by 2. That means that the original number has to have a 2 in there in order to work. Has to. So that means that P must also be an even number. Sorry, I should have an S on there, which means P squared is an even number. That means that P is also an even number. Oops. Now, this sentence right here, these 2 sentences right here, this is kind of using outside understanding of numbers, right? This isn't anything we've talked about. This is something we're literally talking about right now. And it's important because I have to make sure that we are okay with this point, that if you have an odd number and you square it, it's not going to all of a sudden become an even number, because the odd number that you start with, it has to have a factor of 2 in order for the result to be divisible by 2. All right. So if I have an even number like 6 and I square it, well, 6 is 2 times 3. So if I square 2 times 3, I get 4 times 9. But what I'm really getting is 2 times 3 times 2 times 3. So this is clearly divisible by 2 because there's a factor of 2 here. So this is even. Duh. All right. But if it doesn't have, like, let's use 15. If it doesn't have a factor of 2 when you start, it's not going to all of a sudden produce a factor of 2 once I square it. Like, a factor of 2 doesn't just show up. So it's not even every single time. All right. Hopefully I explained that clearly enough and that you feel comfortable with it. All right, let me erase all the highlighting and let's move on with the proof. Okay, so now that I've made this assumption that P is also an even number, then P equals, let's do, let's see, so many letters going on here. Let's just do 2A for some integer A. Okay, cool. So now P is an even number. So here's what that says. If I plug the even number in to my original statement here in particular, this right here, that statement. So 2q squared equals 2a squared, which equals 4a squared, which is going to be q squared equals 2a squared. So q is an even number. From the same argument I just came up with for p, q squared is going to come out even, so q is going to come out even. So q is even, an even number. Okay, now here's the contradiction, and I am running out of space. So here, I'm going to actually give myself some space. I'm sorry, it's just because I have to write so big with this pen. Frustrating. All right, let me, boop. Okay, don't get mad. Boop, boop, boop. Okay, myself a little bit of space. Oops, I'm sorry. I might have to delete it later, but that's all right. For right now, we're okay. Okay, so q is an even number, which means that when we wrote the square root of 2 equals p over q, this is reducible. But that's actually a problem, because we assumed that when we wrote square root of 2 as a rational number, p over q, that it's a fraction that's not reducible. Why would those two have common factors? They wouldn't. And in fact, if it reduces, maybe it reduces to a non-fraction, like a whole number. And that's a problem. That means our original assumption is problematic because we were able to show that there were different integers that we should have used at the beginning to represent square root of 2. And where does that end? It doesn't. It never ends. So this is a contradiction. So this is a contradiction, since PQ is the reduced form. And we're done. Because that means, since we came to a contradiction, that means our original assumption is wrong. And our original assumption was assume radical 2 is rational. Therefore, it's not. It's irrational. In fact, I should probably take a second and write that statement. Oh, I'll have to squeeze it in. Therefore, square root of 2 is irrational. I came to a weird contradiction. Now, as you kind of saw, this wasn't like a super straightforward proof with everything that we have seen in this class. This is using some logical points, understanding how numbers work, understanding that when you say something is in the form P over Q, I'm referring to the reduced form. If I'm saying that 1/3 represents the fraction, why would I instead use 2/6? Right? Like, why would I use a fraction that's not reduced? I would use the reduced fraction. So, especially, like I said, if we run the risk of it possibly reducing down to like a whole number, well, that's not really so much of a problem in terms of the rational element. I just realized that, but that's okay. We're assuming that those two things have no factors in common. All right. We will talk a little bit more about that the fact that they have no factors in common later on in the textbook. But there we go. For right now, that's how we prove it. It is a famous proof. And let's try it again. Let's try another one. Prove that there is no largest prime number. Let me get rid of that weird thing. It's going to give me the keyboard. I'm sorry. Okay. Let's use proof by contradiction. Okay, so that means then we are assuming there is a largest prime number. What this means, by the way, the implication of this example, oops, I'm sorry, is that prime numbers are infinite. We can continue to find prime numbers forever. In fact, this is going to show you how you can produce a new prime number once you have a very large prime number. Okay, so assume, sorry, let me scroll down a bit. Oh, why did that come back? I'm so sorry. It's because I bumped it again. Assume there is a largest prime number. Now remember, a prime number is a number that's only divisible by itself in 1. Okay. That means we'll call it, here, sorry, comma, call it P sub n. I don't know why they use P sub n. That's weird. I'll just call it P. No. I'll call it P sub n because they're using the sub notation because they're referring to like the nth prime number. Okay. Hence, we can list, we can list all the prime numbers starting with the number 2, 2, 3, 5, 7, 11, blah, 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 all the way down till we finally hit P sub n, which is going to take a while. Okay, so we can list all the prime numbers. Now, consider this special number. I'll call it R. And let's say R equals 2 times 3 times 5 times 7 times 11 times ... all the way times P sub n plus 1. Now, none of the prime numbers that we have divides R. So none of the prime numbers divide into R because of the plus 1. It ruins it. So R is prime. But R is bigger than P sub n because it's plus 1. So we have a contradiction, which is a contradiction because now I just showed, oops, see, I'm running out of space again, mainly because I just put some space, which is a contradiction because I just showed that there's a bigger prime number than P sub n. So there is no largest prime. I'll put my end there because I'm running out of space. There's my little box. Boop, boop, boop. Okay. We did it. Now, I'm going to go ahead and adjust this back, which might be a little bit weird, and I'm sorry for that. Okay, I know. Because I just need more space. And here we go. There's something called a biconditional statement. And we talked about this. The biconditional says that P implies Q and Q implies P. That's this statement right here, that both of those happen to be true. And we use in biconditionals this phrasing, if and only if. So if you say if and only if, that's saying that both directions, if P then Q and if Q then P, happen to both be true. So if n is an integer, then n is odd if and only if n squared is odd. In other words, if n is odd, then n squared is odd. I don't know why my words are blending together so much. Spaces, Allison. There we go. And if n squared is odd, then n is odd. That's what this is. But here's the cool part. We actually have already showed both of those. If you look back at our previous examples, we did show that when n is odd, n squared is odd, and that when n squared is odd, n is odd. So both of which we have shown. Both have been shown in previous examples. So we're done. We've proven the biconditional statement is true because we showed both ways are true. So you might see some biconditionals, and there you go. You have to do both directions. N is odd implies n squared is odd, and n squared is odd implies n is odd. That same both direction format. Okay, let's look at an example of a problem proof. All right. What is wrong with this proof? And this is a proof that 1 equals 2. And a lot of teachers like to show this to like blow people's minds, but there's a problem. So let's see. They start with A equals B, and that's our premise. Okay, A equals B is our starting point. We have two numbers, and what they do is they multiply both sides of our equation by A. So we're left with A squared equals A times B. Then they subtract B squared from both sides of the equation. So we have A squared minus B squared equals A times B minus B squared. Then they factor the left side and they pull out a GCF on the right side. And then they divide both sides by A minus B because both sides have this in common. All right. And they're like, cool. And then we get A plus B equals B, which means since A and B are equal, they substitute 2B in for A. And they say, okay, so that's B plus B equals B, or 2B equals B. Or if we divide both sides by B, 2 equals 1. Okay, but here's the problem. Here's where the proof falls. In fact, it's where I just highlighted. A minus B. A minus B equals 0. Why? Our premise, the two numbers are equal. So we can't divide by 0. Which means they can't do step 4 to 5. That's a false step. So we're done. That's what's wrong with the proof.